All right, welcome back, everybody. Today we're actually going to be doing two sections that I've kind of merged into one. So it's sections 8.4 and 8.6. But the book has those sections split up into two-dimensional vectors and three-dimensional vectors. And the reality is that vectors can be any dimensional. So it's actually better to think of them and discuss them in a more general context and then look at how they behave in two dimensions and three dimensions. So what I've done is I've basically merged these two sections into one and rearranged things a little bit. So if you're following in the book, these sections are going to be kind of like interspliced and mixed around and so on and so on. There's also some notation later on in the section that I pull from Stewart's calculus textbook because that's what you'll use when you take Math 7, Math 8, and so on at SMC. So let me go ahead and get the slides going. There we go. And let's see what we're in store for today. All right. So first off, we're going to talk about three-dimensional space, just to get a feel for how we describe three-dimensional space, how to talk about points in three-dimensional space, and so on. Then we'll get the midpoint and the distance formulas for three-dimensional space. Then we'll talk about vectors. And again, like I said, vectors can be any dimensional. So we're going to talk about them in generality and then use examples in two dimensions and three dimensions. Then we'll talk about geometric vector arithmetic, algebraic vectors, algebraic vector arithmetic, properties of vectors, basis vectors, unit vectors, and then a physics application at the end. So just a little bit of a fair warning, this will be a little bit of a long lecture, but I'll try to keep it short if I can. So first, let's talk about three-dimensional space. So when you're working with the real numbers, the set of real numbers, we can use the real line to visualize what those things are. So on the real line, each point is associated with a real number. Oh, and we denote the real line or the set of real numbers with that fancy r. Now in the plane is denoted by r squared, which is r cross r. And in the plane, each point is associated with an ordered pair of real numbers, two numbers like x and y. And they're ordered meaning x is the first coordinate, y is the second coordinate, and so on. Now, three-dimensional space behaves the same way. That one's denoted by R3 or R cubed, and each point is associated with an ordered triple of real numbers. And we usually use the letters X, Y, and Z. And if I remember correctly, I believe the use of those letters was from Descartes. And if it wasn't Descartes, it was Fibonacci. It was one of those two guys who decided to start using X, Y, and Z to represent variables in the different dimensions. So this is essentially how you define n-dimensional space. So more generally, n-dimensional space is denoted as r to the n, and it's just r cross r n many times. And what this space consists of is all n tuples of the form x1, x2, x3, x4, dot, 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 all the way to xn. So the idea that I want you to take away from this is that even though we often talk about three-dimensional space and two-dimensional space, much of what we discuss can all be extended to any dimensional space. So you should really let your mind wander. And the other thing is this doesn't need to be connected to a physical space. So even though we call it like the real line and the real plane and things like that, these ideas, especially vectors, they don't have to correspond to some physical dimension. They can just correspond to a data point even. And that's something that you'll explore more in linear algebra, and I'll give you a little bit of a taste of it today. So to establish a Cartesian coordinate system or rectangular coordinate system, in three-dimensional space, we're going to fix a point O called the origin, and we're going to pass three perpendicular lines through it. And those are going to be the coordinate axes. So each axis represents a single real line, the x-axis, the y-axis, and the z-axis. And the positive direction of the z-axis is determined by what's called the right-hand rule. So here's a picture of it right here. This is what three-dimensional space looks like when we try to depict it on a on a two-dimensional plane. So a couple things to notice. This is the x-axis right here. This is the y-axis right here. And then this is the z-axis going up like so. So this is actually much more intuitive than you might think, but Basically, this cross, the green cross that I've written here, that indicates what the XY plane is. And essentially, through all of your math education previously, you've been working in the XY plane. This is the positive direction of the x-axis. This is the y direction. And then the positive direction of the z-axis is determined by the right-hand rule. So if you want to know which way is up, basically you use your right hand, and if you kind of clench it like so, or kind of curl your fingers inward, your pointer finger is going to point in the direction of the x-axis. Your curled fingers are going to point in the direction of the y-axis, right? There's y, there's x, and then your thumb will point in the positive direction of the z-axis. So that's kind of how you can tell which way is up in three-dimensional space, because you do have to make a choice. You have to make a choice if you want up to be that way or if you want up to be that way. The reason that we choose it this way is because it makes things much more intuitive. So for example, let me look at this, let me emphasize this right here. Okay, x, y. So that is the xy plane. And if you could kind of think about taking this thing and rotating it like so, you'll see that you get the usual xy plane if you're looking at it straight on. And so the z-axis essentially comes out of the paper toward you. So anytime you draw an xy plane on the whiteboard or on your paper, you can think of the positive direction of the z-axis as coming out toward you. That's the up direction. All right. And again, if you forget, you can always use the right hand rule as it's indicated here. But this is essentially how we orient three-dimensional space. All right, now if we're given a point in three-dimensional space, maybe we'll call it the point A, B, C. Oops, come here, there we go. A, B, C. Then what each coordinate represents is the directed distance from the origin along that respective axis. So A, B, and C are telling you how far to go in each dimension and which direction. Do I go in the positive direction, the negative direction, and how far? And those components, those coordinates tell you all of that information. Now, if you're given any point P in space, any point P, like this one right here, it determines a rectangular box, like shown below. And that box it shows you all the different kinds of projections, which we're going to talk about next. So let me look at this point, for example. So this point right here, I'm going to zoom in. Here we go. This is the point -4, 3, -5. So what those coordinates say is move in the negative direction 4 units along the x-axis, move in the positive direction 3 units along the y-axis, and then move in the negative direction 5 units along the z-axis. So you can kind of think of it like this. Let me get my pen here. All right, so we want to go, actually, I'll use this. Yeah, so we want to go this way 4 units. Notice that's the negative direction of the x-axis. So we're going to go 4 units that way. Then we're going to go 3 units this way. That's 3 units in the positive direction of the y-axis. Then we're going to go down 5 units along the z-axis, and that will lead us to the point. That's how we describe what that point is, -4, 3, -5. Let's do this one as well. So this is the point 3, -2, -6. So we go 3 units positive direction along the x-axis, -2 units along the y-axis. So we're going in the negative direction 2 units. And then we're going to go down 6 units. So the negative direction of the z-axis, 6 units. And that's how we describe what these points are. They're just telling you how far to go in each subdimension. Okay. All right, now, points that have a 0, z coordinate lie in what we call the xy plane. So you can think of a point like, I'll just make one up real quick. Think of a point like 1, 2, 0. Because the z coordinate is 0, there's no vertical displacement at all in the z direction. So you're going to be on the xy plane. And then these two coordinates here tell you where you're going to lie in the xy plane. Now, because any point in that plane will have a 0, z coordinate, the equation for that plane, the equation for the xy plane is z equals 0. So in three-dimensional space, you've got 3 coordinates, right? X, Y, and z. Well, any point in the xy plane will have z coordinate 0, and x and y can be anything you want. So the defining equation of that plane is z equals 0, which makes sense, right? Because it's not dependent on x and y. It's only dependent on z, and we just require that z is equal to 0. Now, I realize I forgot to include the third one. That's okay. Uh, so the next one is this. Maybe you can figure out what the third plane will be. Oh, get rid of that. So points that have a y coordinate of 0 lie in the xz plane. So for example, let me come up with one here. Think about the point 1, 0, 5, right? So the y coordinate is 0 for that point. So that means that this point lies in the xz plane because the x and z coordinates are something else. But all that's important is that the y coordinate is 0, and that's why the xz plane has the equation y equals 0. And I realize I forgot it on the slides, so I'll include it after this, but points where the x coordinate is 0, those lie in the yz plane, and the equation of that is x equals 0. I don't think I have that here, do I? Oh, no, I do. I just put it on the next slide. That's all, just to give myself some space. Here we go. So points with an x coordinate 0 lie in the yz plane, and that the equation of that plane is x equals 0. All right, now if we drop a perpendicular line from the point ABC to, for example, the xy plane, then we get a point with coordinates a, comma b, comma 0. And that point is called the projection of the point P onto the xy plane. So I'm going to zoom in here. So here's the point ABC. And if we project that point downward onto the xy plane, we'll get the point AB0. So ABC became AB0 because we basically dropped the z coordinate down to 0. And that's what we call a projection onto the plane, the xy plane, just like that. And you can do projections onto any plane. And we're going to talk more about projections in the next section, actually, in 8.5, when we talk about the dot product. But that's what that is. That's the projection of the point. All right, so now we're going to get some generalizations of some really handy formulas. The first one is the midpoint formula. And you've seen this formula before for 2 dimensions, for the midpoint of a line segment in R2, or the xy plane. And this is the generalization to 3-dimensional space. So the midpoint of a line segment from a point P1 to a point P2 in 3 space is given by this formula right here. That's the formula. And it makes sense when you think about why the formula looks the way that it does. So here what we're doing is we're taking the average of the x coordinates. That's giving us the middle, right? The middle of the x coordinates. And then here we're taking the average or the middle of the y coordinates. And then now we're also going to take the average or middle of the z coordinates. So we're basically finding all of the midpoints of those line segments in each subdimension. And not too bad, right? It's really just a natural generalization from 2 dimensions to 3. It turns out that you can generalize it this way to any number of dimensions. And you should let your mind go wild and imagine things. But if you've got a point that's in 100 dimensional space, or sorry, if you've got 2 points that are in 100 dimensional space, you can find the midpoint of the line segment that connects them using this formula. You just do, x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2, maybe t1 plus t2 over 2 if you want the 4th dimension to be time, for example. And then you can just keep going and going and going. So the midpoint formula, very natural, just extends from what you already know, and the intuition is still there. All right. The good news is that the distance formula similarly generalizes. And if you've got 2 points in 3 space, then the distance between those 2 points is given by, frankly, the Pythagorean theorem. So you're going to do the difference in the x coordinates squared plus the difference in the y coordinates squared plus the difference in the z coordinates squared. And then you take the square root of that result, and that will give you the distance between those 2 points, P1 and P2. Uh, Kind of like I just mentioned, this is just a generalization of the distance formula from 2 dimensions to 3 dimensions. And in fact, it generalizes this way to any number of dimensions at all. So even if you're working in 4, 5, 6, 100, a billion, a trillion dimensional space, you just keep adding these terms, the x2 minus x1, y2 minus y1, z2 minus z1, all those squared, right? And you just keep doing that. The proof is actually just as simple as the proof in 2 dimensions. It just uses the Pythagorean theorem. Oops, there we go. Just uses the Pythagorean theorem, but now you're going to have to use it twice. We won't do it here. I don't remember if the book has a proof of this or not. I know that Stewart's book does. But again, you can try it yourself. Try it yourself, pick 2 points in space, and basically find the length of the hypotenuse that is the line segment that connects them. Find the length of that hypotenuse of a triangle, and that's how you do it. How do you find lengths of hypotenuses? Pythagorean theorem. Okay, so let's practice this. And this one I think you'll be able to do right away. So I want you to think about how you would do this one and then just try it on your own. Find the midpoint and the distance between these 2 points, -3, comma 4, comma 1, and 5, comma 2, comma 6. So think about it, try it on your own, and then we'll do it together. All right, let's do it together. So the midpoint is super simple. You just add up the corresponding components, -3 plus 5, 4 plus 2, 1 plus 6, and then divide all of those by 2. And then that will give you the midpoint. So the midpoint of the line segment connecting those 2 points is this right here, -1, comma 3, comma 3.5. And then the distance, you can just use the formula. Here you've got x2 minus x1, y2 minus y1, z2 minus z1, square all of those terms, and then take the square root of the sum. And you get that the distance is the square root of 93. And that's pretty much it. Not too bad, right? One of the things I like about these is if you just remember the Pythagorean theorem, you get the distance formula for free. And if you remember what an average is, you get the midpoint formula for free. And it works in any dimension. So you've already got that for when you get to like linear algebra, or if you ever want to work in higher dimensions, which many of you will. Many of you will. We'll talk more about that later. All right, so that's the crash course in three-dimensional space. Now let's talk about what vectors are. If you've taken a physics course, then you've probably seen these before in some capacity. And I mean, honestly, they're just the bread and butter of physics. And for those of you that go on to take Calc 3, which I hope is all of you, you're going to love it because when you get to Calc 3, you get to start doing vector calculus. And the things that you can do with vector calculus are just out of this world and in this world. Like, it's just absolutely amazing. So, I hope you enjoyed as much as I did. But let's get to the definition. What is a vector? So, a vector is a quantity, but it has both direction and magnitude. So, this object is a bit different than stuff you've been working with in the past. It's still a quantity, but it's a quantity that has two values associated with it. One of them is a direction, and one of them is a magnitude. So we can talk about essentially how far do you want to go in some direction? That's the idea. So when you think about a vector, you should intuitively think about somebody saying how far you're going to go and in what direction you're going to be traveling. That's basically what a vector is. So vectors are, because of this, vectors are often represented by an arrow or a directed line segment. We're going to play around with these a lot in just a minute. So vectors are often just given as arrows, and they'll basically say which direction you're supposed to go. And then what you can do is you can let the length actually represent how far you're supposed to go. We'll see that in the next slide. How do we denote these vectors? So you can either denote vectors by a bold letter, just to distinguish them from scalars, which we're going to talk about next. Or you can, because it's hard to write bold when you're freehanding things, you can also just write it with an arrow above the letter. Let me zoom in a bit. There you go. So you could write, if you want to talk about the vector v, you can just write a v and then put an arrow over the top. and that's also acceptable notation, and everybody will know what you're talking about. Um, Now, so this is one of the reasons why I wanted to merge these two sections and just talk more generally about this idea. So vector is just a direction with a magnitude. That's all it is. Notice it has nothing to do with dimensions or being in the plane or being in space or anything. It's literally just a direction and a magnitude. So because of that, vectors exist in any number of dimensions you want. You can even talk about vectors that are in non-integer dimensions, but that's much later on, much later on. And the truth is that in many modern applications these days, vectors require high dimensional spaces to be considered. And stuff gets really interesting when you start to consider infinite dimensional spaces. Yes, you can talk about infinite dimensional spaces, and that's when things get super fun. But again, when you're thinking about vectors, I don't want you to think that they only exist in 2D and 3D. They exist in any D, any D, right? And if you want to go into things like data science or computer science or even data analysis, quantum physics, all these things, oftentimes the spaces that you're working in are high dimensional, hundreds, thousands, millions of dimensions. And if you haven't thought about that before, that's totally fine. Now is a good time to just let your mind kind of wander and be like, man, what is 10 dimensional space? What is 11 dimensional space? How does that even make any sense? Well, when you get to linear algebra, you'll get to explore it in great detail. Great detail. It's really fun. Um, okay, so if a particle moves from a point A to a point B, then the corresponding displacement vector has an initial point A and a terminal point B. Sorry, that should be bold right there. Terminal point B. And what we do is we write V equals AB with an arrow over the top. So in essence, a vector is, again, just saying where to go and how far to travel, which direction to go and how far to travel. So here, let me erase this real quick. This is basically what a vector looks like. The vector leading you from point A to point B. Makes sense, right? Now, in this figure, notice that the vector v and the vector u have the same direction and they have the same length. So because these two vectors have the same direction and length, they are equal or equivalent vectors, and we write v equals u. And this is an important detail which I get to in a couple of slides, but just because these two vectors are not literally on top of each other, that doesn't mean that they're different. Because remember, a vector is just direction and magnitude, and both of these vectors are saying which direction to go and how far to go. And I'm sorry, they're saying which way to go and how far to go, and that data is the same for both. So because of that, those two vectors are equal vectors, equal vectors. Now, the zero vector, which is denoted by a bold zero, that's the vector that has length 0, and it's the only vector with no specific direction. So that's the one thing that's special about it. It's the one vector that has no specific direction, and it's the only vector with 0 length. Okay, so how do we add these two things together? So now that we have vectors, we have these new quantities, we want to be able to play with them and do things with them. So first, let's talk about addition. How do we add two vectors? So if we got two vectors, u, which takes you from A to B, and v, which takes you from B to C, then the sum of those two vectors is written as so, and it's the vector that takes you from A to C. And how do we view this geometrically? We view it using what's called the triangle law. So if you want to talk about u plus v, that means travel in the direction of u as far as u says to go. Then from that point, travel in the direction of v as far as v says to go. And the point that you end up at right here, this is where we started, right? We started back here and we went this way along u and this way along v. There we go. That's the terminal point of the sum. So the vector sum basically tells you how to cut across the field, cutting across the field there, going straight from the initial point to the terminal point of the vector v. The initial point of u to the terminal point of v. And so that's angle addition, that's vector addition. You're pretty much just adding the directions and the lengths in that way. All right, let me erase this. we're going to see this later when we look at the properties of vectors, but it turns out that vector addition is commutative. So it doesn't matter if you do u plus v or v plus u, the resulting vector will be the same. And that's indicated down here using what's called the parallelogram law. So here at the bottom, I went u, v, and this is where I ended up, right? Ended up at this point. But notice that if we instead did v first and then u, we still end up at the same point. So that means that the vector u plus v is equal to the vector v plus u. And that's pretty much it. So geometrically, it makes sense. And you can prove it algebraically as well, which we're going to see in a couple slides from now. All right. So let's do an example. Let's draw the sum of the vectors a and b below. And I'm going to cheat just a little bit and use my technology here so that I don't have to, my lines won't be as wiggly. But here's the vector a. I'm just going to trace it. Okay, and then here's the vector b. All right, and if I want to do the sum of those two vectors, let me copy this here. Here's a. Actually, let me do that. There we go. And then here's b. There we go. So this is the vector b. All right, so basically we went this way along A and then this way along B. So the resulting vector sum is the one that starts here and goes here. There we go. So this is A plus B, and these are all vectors. So since I can't write bold, I'll use little arrows. And that's A plus B. So that's how you can do it. Super simple, super intuitive. It's literally just going from start to finish, and then from there to the next point, from there to the next point. So maybe if if you've ever thought about like Google Maps or how Google Maps works or calculates the optimal trajectory for your trip, vectors, vectors. That's how. Okay. All right, so now we need to distinguish between something here. So we've been talking about vectors. So there's another thing that we have to talk about, which are called scalars. And you've been working with scalars for your entire math education. Scalars are just real numbers, or they could be complex numbers. Either one are totally fine to use. We talked about complex numbers in this course, so you can use complex numbers, or you can use real numbers. Which you use really depends on the application and the context, but either of them are scalars. And if you ever get to take a class called abstract algebra, you can generalize this notion even more to just, frankly, just fields of scalars. I mentioned fields a little bit in, oh geez, what was it, 8.3? Yeah, section 8.3. But you can talk about different fields of scalars. They don't always have to be a real number or a complex number. Now, there's an important distinction here to make, and this is one of the critical ideas. A scalar is not the same thing as a vector. So let me emphasize that here, right? So a scalar is just like a number. It's got one like value associated with it. It's just a number. Let's use real numbers for intuition. It's just a real number, right? A vector is not a scalar because a vector has two values associated with it. It's got a direction and a magnitude. So it's basically got a length, but it also has a directionality associated with it, right? So scalars and vectors are not the same objects. They're not the same objects, but we can talk about how these objects play together, and we can define meaningfully what it means for these things to play together. And we're going to do that right now. We're going to define what it means to multiply a vector by a scalar. And so this is what's called scalar multiplication. So if k is a scalar and v is a vector, notice that v is bold, but k is not. That's to help us distinguish between a scalar and a vector. So if k is a scalar and v is a vector, then the scalar multiple, k times v, is the vector whose length is the absolute value of k times the length of v. That's what it is. So literally, in essence, these scalars are just stretching or shrinking the vector. That's what they're doing. So for example, if k is greater than 0, then kv is a stretching of that vector v, but the direction will be maintained. So the direction will be maintained. Oh, I'm sorry, if k is greater than 0, it could shrink it. I apologize. It could shrink or stretch, but we're not changing the direction. We're not turning anything. So it's like, here's my vector v. You can kind of see it there. I can either shrink this pen or stretch the pen or shrink it, but the direction is not changing because k is positive. Now, if k is negative, you can still stretch or shrink this vector, but the direction is going to reverse. I can't do it. There you go. Direction is going to reverse. Boom. And that makes sense too, right? Because if k is negative, then we're multiplying by a negative number, and so that's going to basically turn the whole vector around, and it will change the length if k is anything with a magnitude different than 1. Now, if k is 0, or if v is the 0 vector, oops, see, that should be bold right there. There we go. If v is the 0 vector, then kv is the 0 vector. See, that should be bold too. I'll fix that in the slides. Yeah, there's a distinction between scalars and vectors. They are not the same thing. So it's important to use the notation appropriately and consistently. So I apologize for that. All right. Okay, so what is a parallel vector? So we say that or parallel vectors. What are parallel vectors? We say two non-zero vectors are parallel if they're scalar multiples of one another. So in other words, if you can write, for example, W equals KV, then W and V are parallel. And this is the definition of parallelism, that one is just a scalar multiple of the other. Also, we can talk about negative vectors, right? So the vector negative V right here is defined as multiplying the vector V by the scalar -1 to turn the direction around. And because the scalar is -1, it does not change the length of the vector, it just changes the orientation by flipping it, literally the opposite direction. So it's like the opposite of V. And it's called the negative of V, or the opposite of V. So down here I have some examples of how you can change V, but still keep a bunch of parallel vectors. So this is the vector V. This is the vector 2v. Notice it's the vector v, but it's been stretched. It's been stretched by a factor of 2, so it's twice as long, but it's in the same direction. So it's like traveling the same direction, but twice as far. That's what that means. Oops, let me keep this one highlighted. This vector right here, half v, that's the vector v, but now it's been shrunk this way, shrunk down. So the same direction, but half the distance. Here's the vector -v. It's the same length as v, but it's just turned around, so now it's pointing in the opposite direction. And then here's the vector -1.5v. So this one is the opposite direction of v, and it's been stretched, so it's going to travel a little bit farther, right? Yeah, going to travel a little bit farther than v. But all of these vectors are still parallel to one another. They're parallel to one another because they're all just scalar multiples of each other. That's it. Every single one of these vectors you can write as a scalar multiple of any of the other ones. So they're all parallel. And that's this right here. All right, now, how do we define vector subtraction? Well, the way we define vector subtraction is by using the negative of vectors. So if we want to talk about u minus v, then we just recast it as u plus -v, right? U plus -v. So this is saying travel in the direction of u and then travel in the opposite direction of v. And that's what's pictured right down here in these two pictures. So check this out. Here's the vector u, and then here's the vector v. But the vector -v is this. So if we want to do u minus v, we're going to do u plus -v. And remember, vector addition basically just means go tail to tip with each vector. So let me repeat this. Here's -v. So if we want to do u minus v, we're going to do u plus -v, and it's going to lead us right here to that point. Oops, there we go. So this is the vector, u minus v, picked out right here. And that's the idea. So again, very intuitive, very natural. It's just telling you where to go from each point. All right, now let's practice this. Again, I'm going to use my use my technology to my advantage here. So I've got two vectors, a vector A and a vector B, and I'm going to reconstruct the vector A minus 2B, or I'm going to try to right here. So let me copy these. Okay, so here's the vector A, here's the vector B. Right, let me pick this out, move these around. There's A, there's B. I'm going to forget if I don't label them. Here's A, here's B. Now, we're trying to do A minus 2B. So let's find 2B first, and then we'll take its opposite. So 2B is going to be like doubling B. There's two of them. And if I put them right here, oops, there we go. So this right here, this is the vector 2B. Oops, I want this. So here's the vector 2b, literally just 2 times b. Now I'm going to turn that thing around, or I'm going to try to here. I'm going to turn this thing around. Let's see. Okay, I'm going to try to do it without changing the size, but it's hard to do. Come here. Here, I guess I could compare it to this to make sure the size is about the same. There we go. Okay, that looks about right. That looks about right. Okay, so there's 2b. Let me relabel it. Or negative 2b, my bad. Negative 2b. All right. And now if we want to do a plus negative 2b, we would do the vector a, which is right here. And then we're going to do the vector negative 2b, which is right here. There we go. And so the vector a minus 2b is going to be this one right here. Actually, let me move this out of the way. That up there. Move that up there. There we go. A minus 2b. There we go. Nice. Matches pretty well. So there's geometric vector arithmetic. That's how you do arithmetic with vectors geometrically. Super fun, super intuitive. All right, now let's talk about algebraic vectors because we would like to be able to work with these algebraically and not just have to use like a compass and a straight edge and like rotations and so on. And again, math doesn't need to be visual. That's something I haven't said before, but everything that we talk about in math doesn't need to be visualized. It's just that visualizing math gives us a nice intuition for what's going on because we have eyes, or a lot of us have eyes. So when we can see things, it makes it easier to understand. But all of the concepts we're talking about do not require vision whatsoever. So you should think about that sometimes. Like, how could you explain a mathematical concept to somebody who is visually impaired or somebody who's been blind since birth? They can still do math and they can still do meaningful mathematics and they can make sense of mathematics, even if they don't have vision to see all these things. So anytime you think about like something in math and you're like, oh, the picture is so easy to understand, it's like, yeah, but we always need a way to describe it non-visually. So that's what we're going to do right now. Let's talk about algebraic vectors. How can we describe these things algebraically? And here's how we do it. Remember, vectors can be any dimensional, doesn't have to be 2 or 3. So let's let V be an n-dimensional vector. Then we can represent V like so, right here. It's basically an ordered list of components. But the difference here, I'm going to zoom in a little bit. The difference is that now we're using these angle brackets. So these aren't parentheses, these are angle brackets that look like this. And this is just a common convention to denote a vector. And these components all talk about which direction to go and how far in each subdimension. So you can almost think about it as similar to like, oh, move this far in this direction along the x-axis. Move this far in this direction along the y-axis. This far in this direction along the z-axis, and so on and so on. So that's what each of these components are telling us what to do. Again, it can be any dimension, right? It doesn't need to be 2 or 3. It can be any number of dimensions. That's why we're doing this in total generality. Those numbers, A1, A2, yada, 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 those are scalars. So they could be real numbers or complex numbers, and they're called the components of the vector. And like I mentioned a second ago, the components just say the distance and the direction of travel in each subdimension. Now, for just for notational purposes, we denote the space of n-dimensional vectors by v sub n. So v sub n is basically a set with some properties associated, but when we write v sub n, we just mean n-dimensional vectors. That's it. Vectors that have n components. So for example, do I say it here? Yeah, I say it right here. In this course, we're only going to be dealing with 2 and 3-dimensional space. So our points will be of these two forms, either xy or xyz. And then we're only going to be dealing with 2 and 3-dimensional vectors in this course. But again, it extends to any number of dimensions. So our vectors live in V2 or V3, the space of 2-dimensional vectors, or the space of 3-dimensional vectors. And they're of the form AB or ABC. And again, I know I keep saying it, but all of this extends to higher dimensions, so let your imagination run wild. And the further along you go in mathematics, you'll get to explore these much more interesting ideas in higher dimensions. And that's when it gets really, really fun. So I encourage you to just like zone out or veg out or trip out on thinking about higher dimensions. It's fun. Okay, so now let's talk about position vectors. So if we've got a vector A given by the components A1, A2, A3, but the initial point of this vector lies at the origin of the Cartesian coordinate system, then A is what we call a position vector. And the terminal point of this vector is the point A1, A2, A3. And that's one of the reasons we call it a position vector. So a position vector basically has a tail at the origin. And in essence, it tells you how to go from the origin to that point, A1, A2, A3. The figure down here shows position vectors in 2 dimensions and 3 dimensions. There we go. So that's what a position vector is. How do I go from the origin to the point? That's the position vector. Now, just to reiterate an important detail here with this figure right here, this figure right here with a bunch of vectors in it. So all the vectors in this figure are equivalent. These are all equivalent vectors. They are the same vector, and they're equivalent to the position vector 3, 2, whose terminal point is the point 3, 2. So let me zoom in on this. I'm going to use red, I think. Yeah. So this vector right here that I'm tracing in red, maybe a little more precise. There we go. Okay, so this vector in red, that's the position vector for the vector 3, 2. And it's the position vector because it starts at the origin and it tells you how to get to that terminal point 3, 2. But all the vectors on this picture are equivalent vectors. So notice this, if I take this vector and I move it over here, same length, same direction. Or if I move it over here, same length, same direction. If I move it down here, same length, same direction, same length, same direction, same length, same direction. So all of these vectors, even if I move it anywhere, those vectors are all equivalent. They're equal vectors. This is what makes them different from points. So you got to remember, points are not vectors. There's a difference between a point and a vector. And the connection between those, the connection between points and vectors is position vectors. Position vectors have components that are equal to the coordinates of a point. There we go. So what's common about all these vectors? The thing that all these vectors have in common is that the terminal point is reached by moving 3 units to the right and 2 units upward. That's what a vector is, right? Direction and magnitude. So all the vectors that you see on this figure, they're just representations of the same vector. They're representations of the vector 3, 2. The vector 3, 2 says, hey, go to the right 3 units and then go up 2 units. That's a vector. That's why these are all equivalent vectors and they have the same components. All right. So how do we go from points to vectors? For example, if we've got 2 points in space, how do I find a vector that leads me from point A to point B? This is how. So let's say we're given 2 points. Point A is x1, y1, z1. Point B is x2, y2, z2. Then the vector AB is given by this right here. So you do x2 minus x1, y2 minus y1, and z2 minus z1. Now, a couple of notes about this definition. The order is important because remember, vectors have an initial point and they have a terminal point. So this is the vector that leads you from the point A to the point B. And that's why when you're doing these differences here, let me get my pen. Oh, come on, iPad. There you go. Uh, the order of this difference is important because this is telling you how to go from A to B. That's why it's x2 minus x1, y2 minus y1, z2 minus z1. If you want to talk about how to go from B to A, that's a different vector. It's a different vector. It's the opposite of the vector AB, right? It'll be the negative. So if you wanted to talk about the vector that goes from B to A, the order of this subtraction would be switched, and we would no longer be talking about this vector A, we'd be talking about the vector negative A. So for example, negative A would be x1 minus x2, y1 minus y2, z1 minus z2. And this is equal to the vector that goes from B to A. Backward, right? Backward. And everything works out very intuitively and very nicely, which is cool. All right, so now we can talk about how to find the lengths of these things because we were talking about magnitudes and we were talking about lengths and we were saying like, oh, every vector has a length and it's got a direction. So what is the length? I mean, we've been drawing pictures of it and we've been saying that, we can look at the length of that line segment and that'll tell you the length of the vector. But if I have a vector given in terms of components, what's the length? Well, the good news is you've already got the formula because the formula is literally just the distance formula. It's just the distance formula. Um, it's really just, yeah, it's just the distance formula or even just the Pythagorean theorem if you want to take it back to that. So let's say that I've got a vector in 2 dimensions to start. Here, come here. There we go. In 2 dimensions, the vector a1, a2. If I want to know the length of that vector, it's just going to be a1 squared plus a2 squared, and then you take the square root. There we go. And we're gonna use the same notation. Actually, you know what? I realized the book uses this notation, the double bars to represent the length of a vector. But you can use single bars or double bars. It doesn't really matter. Usually the context makes it clear which one you're talking about. Um, I usually prefer to use the single bars until we get into into infinite dimensional spaces because they just agree with what you would call the distance in Euclidean space, right? So in 2 dimensions, it's basically this. In 3 dimensions, it's this. In n dimensions, it's the same thing. A1 squared plus A2 squared plus A3 squared plus A4 squared plus A5 squared dot 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 plus AN squared, and then take the square root of that sum. So same thing as before. What is the length? The length is just the distance. Okay. Now we can talk about algebraic vector arithmetic. So actually, was that, oh yeah. Now we can talk about arithmetic using algebra. So if we've got two vectors, a1, a2, a3, b1, b2, b3, and we've got a scalar k, we can talk about adding these two vectors or subtracting them. And the cool part is that vector addition occurs component-wise. So if I want to add these two vectors together, I add the corresponding components. And if I want to subtract those two vectors, if I want to do a minus b, I subtract the corresponding components. And the resulting vector will be the vector sum or the vector difference. So everything's just component-wise, super simple. Uh, just as simple is scalar multiplication. So scalar multiplication quite literally occurs component-wise as well. So if you want to talk about k times a, you just apply that scalar k to each component, like so. And that's scalar multiplication, shown algebraically. What's really cool is that you can connect it to the geometry. So I just love the connection between algebra and geometry here. And it's just so natural and intuitive. It just makes sense. So let's look at a vector sum and how we can see it, how we can see it manifest geometrically. So let me get my pen here. All right, so here's the vector A, and here's the vector B. So if we want to look at the vector sum, A plus B, what we do is quite literally, we do A1 plus B1, and then A2 plus B2. And that leads us from the initial point of A to the terminal point of B. And that's what it is. So how do we describe that algebraically? We do A1 plus B1 and A2 plus B2. There you go. That's vector addition. That's vector addition. How do you do scalar multiplication component-wise? So if I want to talk about, oh, they used a C here. That's okay. If you use the vector, I'm sorry, if we use the scalar C and I want to talk about CA, what I do is I scale the first component by C and I scale the second component by C, and everything happens component-wise. CA1, CA2. So now I'm going to go from here to here to here. And that's it. Everything gets scaled. Very intuitive. It's nice. Okay, let's do some examples here. And these ones I want you to try on your own. And I'll give you a couple of, well, take a few minutes to try to do all of these on your own, and then we'll look through the work together. So let me lead us off here. Let's start with this vector A, which is 4, 0, 3, and this vector B, which is negative 2, 1, 5. Now, what I want you to try on your own is see if you can find the magnitude of A, the vector sum, the vector difference, the vector 3b, and then try to combine a bunch of stuff. Do 2a plus 5b. So think about this one on your own, try it on your own, and then we'll do it together. All right, now let's do it together. So first, how do we find the magnitude of the vector? We just use the distance formula. Oh, incidentally, I keep saying the distance formula. I should say the distance formula for the position vector, if I wanted to be a little more precise. But in essence, you just square each component, add up those results, and then take the square root, which is exactly what I'm doing here. 4 squared plus 0 squared plus 3 squared gives me 25. Take the square root of 25, I get 5. So this vector A has length 5. How about this one? A plus B. Hopefully you got the same result. You just do everything component-wise. 4 minus 2, 0 plus 1, 3 plus 5 gives us 2, 1, 8. That's the vector sum. Here's the vector difference. Again, everything is component-wise. 4 minus negative 2, 0 minus 1, 3 minus 5, and we get 6, negative 1, negative 2. All right, 3b, scalar multiplication, occurs component-wise. So you do 3 times every component. 3 times negative 2 is negative 6. 3 times 1 is 3. And 3 times 5 is 15. Not too bad, right? And now let's just throw everything together. Let's do a whole combination of things. 2a plus 5b, that means scale every component of a by 2, scale every component of b by 5, and then add those results. So that's what's going on first. 2, 5 gives us these new vectors. And then we add up all the components. We do the addition component-wise, and then we get negative 2, 5, and 31. All right. Now we can talk about properties. So this is another reason why I wanted to merge all these things together, or I mean, merge these two sections together. These vectors can be any dimensional vectors, so they can live in Vn. We're going to say we've got 3 vectors in Vn and 2 scalars in whichever field you want to work with, real numbers, complex numbers. The book separates these into 2 dimensions and 3 dimensions, which is why I don't really like the way that they introduce it, because this holds for any dimensional vectors. But all these properties, they hold for any dimensional vectors. They don't change depending on the dimension. They're just the same for any dimensional vector. So first we have commutativity. That's number 1. And we saw that geometrically earlier. I think we're going to prove it algebraically in just a minute, but vectors are commutative, or a vector addition is commutative. The sum of a vector and the 0 vector is always just that vector again. So a plus 0 is a. We also can do this. We have a distributive property. So scalars distribute over vector sums and differences. So remember, c is a scalar. It is not a vector. So c times a plus b is the same as doing CA and then adding CB. That's the distributive property. You've seen that for years and years and years, right? C just distributes to each term. Another thing here, scalar multiplication is associative. It's associative. So if you want to do the product of two scalars and then multiply it by a vector, that's the same as doing one of those factors times the vector and then multiplying by C afterward. So in other words, you've got associativity here. You can move parentheses around through these products. There we go. Then up here, vector addition is also associative. So if you want to add the two vectors b plus c first and then add the vector a, that's the same as adding a plus b first and then adding the vector c. So associativity holds for vector sums as well. Another handy one, a plus its opposite, a vector a plus its opposite is the zero vector. That makes a lot of sense too, because if a tells me to travel in this direction this far, and negative a tells me to travel the opposite direction, the same distance, I'm going to end up where I started. No change in displacement. I'm back at, I basically like I went nowhere. So going somewhere and then going backward the same distance means you end up where you started. So there's zero change in your location. Right. Next, this next line is the distributive property for vectors. So vectors distribute over scalar sums. So if you want to add two scalars and then multiply that by a vector, that's the same as multiplying each vector, multiplying the vector by each scalar and then adding the result. So again, it's like everything intuitive that you would expect. Everything that just makes sense does actually make sense. We can prove it all geometrically. We can prove it all algebraically. You should try some. We're going to do a few, but you should try them on your own as well. And then lastly, 1 times a is equal to a. So if you multiply a by the scalar 1, it doesn't change the vector in any way. It doesn't change its length, doesn't change its direction. It's just the same vector. Okay, now I thought I proved a couple of these. Maybe I think I'm thinking of the next section. Well, I'll leave this to you. Try it out on your own sometime. Just try to prove any one of these using, say, like V3. Pick vectors in V3, three-dimensional vectors, and try to prove, prove these two. There you go, just for fun. Try it and see what you get. Okay, now that we've talked about vectors in generality, we've talked about them geometrically, we've talked about them algebraically, we've talked about them in n-dimensional space, we've connected them to coordinate systems in n-dimensional space. Now we're going to talk about some very, very important vectors. These are called basis vectors. These vectors are absolutely critical, and you're going to see them a lot in linear algebra as well. Again, this all can take place in n-dimensional space. We're going to look at it in three-dimensional space. So there are these three very, very important vectors in V3, and these are called the standard basis vectors. Standard basis vectors. There's I, which is the vector 1, 0, 0. Notice this is not the complex unit, or this is not the imaginary unit. This is a bold I. And then there's the vector j and the vector k. So let's look at what these things do. The vector I basically says to travel 1 unit along the x-axis in the positive direction. The vector j says to travel 1 unit along the y-axis in the positive direction. And the vector k says to travel 1 unit along the z-axis in the positive direction. So I, j, k basically say to go 1 step forward in each one of these subdimensions. That's what they are. They're called the standard basis vectors. They have unit length, so they're only length 1, and they point in the positive directions of the x, y, and z axes respectively. Now, the reason these are so important is because of what's in the box down here. Every vector can be written in terms of these three basis vectors. So any vector you've got, you can decompose it into a vector sum that takes use of these three vectors instead. So you can kind of like peel away the details of these vectors and these basis vectors pop out. We're going to see an example right now. So for one, we can rewrite, again, these are equal. So before I get to that, these are equal. So these are two equivalent representations, like symbolic representations of this vector. So the vector 3, -1, 10 is the same as 3 times the vector I minus, or I should say plus -1 times the vector j plus 10 times the vector k. So this vector sum, or this vector combination, I'll say, this linear combination, is the same as what's over here using the brackets. It's the same thing. Because remember, think about it this way. What does this say? This vector says to travel 3 units in the positive direction along the x-axis. That's what this says. Then it says to go backward 1 unit along the y-axis. That's what this says. Then it says to travel 10 units in the positive direction along the z-axis. That's what this says. So you can decompose vectors into these linear combinations of these basis vectors. That's the big idea. And you're going to see that a lot in linear algebra. More generally, or maybe more expandedly, if we're given a vector A that has components A1, A2, and A3, first we can use vector addition to pull it apart into 3 separate vectors. A1, 0, 0, 0A2, 0, 0, 0, A3. Right? If I were to add those 3 together, I would end up back here again. Then, using scalar multiplication, the definition of scalar multiplication algebraically, we can factor out a1 from this first vector. So let me erase this here. Yeah. So if we factor out a1 from the first vector here, we'll get a1 times 1, 0, 0. If we factor out a2 from the second vector, we're going to get a2 times 1, 0, 1. And if we factor out a3 from this third vector, we're going to get a3 times 0, 0, 1. There we go. But remember, 1, 0, 0 is the basis vector I. 1, 0, 1, I'm sorry, 0, 1, 0 is the basis vector j, and 0, 0, 1 is the basis vector k. So again, you can write any vector in terms of these standard basis vectors. So really what's happening is those components, A1, A2, A3, are where like most of the information is contained. It's in those scalars. And the vectors are really just talking about traveling in a certain direction. Pretty cool stuff. Okay, so let's try this. This is one I want you to try on your own first, and then we'll do it together. So let's say I give you the vector A, which is I plus 2j minus 3k, and B is 4I plus 7k. Then what I want you to try to do is compute the vector sum 2A plus 3B and write it in terms of I, j, and k. So think about it for a minute, and then try to work it out on your own, and then we'll do it together. All right, here we go. So we can use all the properties that we were just talking about before. We know how to do 2a and 3b. That's just scalar multiplication. 2 times the vector a, 3 times the vector b. Distribute, because like we saw, you can distribute over vectors. Scalars distribute over vector sums. That's the distributive property. So we get 2i plus 4j minus 6k, and then we get 12i plus 21k. Now, all we have to do is combine like terms. That's all we really got to do at this point. It's just so natural. It's beautiful. Let's see. 2i plus 12i is 14i. 4j plus 0j is just 4j. Negative 6k plus 21k is 15k. And that's the result. So the vector 2a plus 3b really says travel 14 units in the I direction, 4 units in the j direction, and 15 units in the k direction. That's what it says. Oh, let me take that off. There we go. All right. Okay, so we're getting through. I know this is long. Try to hang in there. If you want to take a break, you can take a break. We're going to move on to a new concept right now, but we're almost through. Almost through. So next we got to talk about unit vectors and how to find unit vectors. We've already seen a couple of them. I, j, and k are unit vectors, but a unit vector is just a vector whose length is 1. That's really all it means, length 1. And if you remember what we were talking about in section, what was it? Oh, it was A.11. I keep saying 8.3, but I mean A.11. Remember, unit basically means 1. So a unit vector is a vector that has length 1. And we like unit vectors because we can essentially count with them. We can count with unit vectors. We call them the unit, and we count how many there are. So what we're going to do now is we're going to learn how to actually find unit vectors in the direction of any vector. And it's not so tricky. It's not so tricky. If we're given any non-zero vector, then we can normalize it. Normalizing it means to find a vector that's the same direction, but with unit length. Same direction, but with unit length. So if I give you some vector, any vector at all, call it A, what is a vector that's that same direction, but only goes 1 unit in that direction? And the way that we do it is we just take the vector A and we divide it by its length. That's it. And that will give us a unit vector in that direction. So sometimes we'll use U to indicate unit vectors, but you don't have to. Another way of thinking about these unit vectors is that it's the vector A times the reciprocal of the length. Either way works. It's really just taking the vector A and dividing it by its length. And this will indeed give you a unit vector, and that's the calculation down here at the bottom. What's the length of this vector U that we just constructed? It's the length of the vector A over length A. But using properties of absolute values or just properties of distances, you can split this up through the fraction and you'll get A over the length of A, which is just the length of A over the length of A, which is 1. Notice also that we still got a scalar from this calculation. So we wanted to compute the length of U, and we got a scalar, not a vector. Because again, length is a scalar, it's a number, it is not a vector. So it makes sense that we should get a scalar as a result. All right, now I want you to try. So see if you can find a unit vector in the same direction of the vector 2i minus j minus 2k. Try it yourself, and then we'll do it together. All right, here we go. So the first thing is we need to find the length. So we'll compute the length of this vector using the distance formula. We're going to have 2 squared plus negative 1 squared plus negative 2 squared. Add those up, you get 9. Square root of 9 is 3. And so that's the length of this vector 2i minus j minus 2k. Now, if we want a vector that has unit length, but it's in the same direction, we just divide 2i minus j minus 2k by 3. So that's what I'm doing here. I'm multiplying the vector by 1/3. So we get 2/3 I, negative 1/3 j, negative 2/3 k, and there it is. So that vector has the same direction, but it's unit length, which is really handy because now we could just count by those things. We could count by that unit vector to say how far we want to go. Okay. See, maybe now this is where I should have said, I should have said take a break. But now we're going to talk about physics applications. So yeah, if you do want to take a break, now's a good time to take a break. Um, so vectors are used extensively in physics and engineering applications because force is a vector quantity. If you ever thought about forces in any capacity, it's a vector. It's got a magnitude and it's a direction. Force is exerted in some direction with some amount of strength, you could say, right? So yeah, there you go. It's a vector because it has a magnitude, usually measured in pounds or newtons, and it has a direction measured in meters, feet, inches, centimeters, kilometers, whatever. Now, if you've got several forces acting on an object, then the resultant force on the object is the vector sum of all the forces. So you could have a whole bunch of things happening to an object, a whole bunch of forces. And if you add up all of those vectors, that's the resultant force on the object, the vector sum. So we're going to do an example of this right now. Classic example. So let's say a 100-pound weight is hanging from 2 wires as shown. we're going to find the tensions, which is a force, the tensions T1 and T2 in both wires, and we're going to find the magnitude of the tensions. So in essence, what we are looking for is we are looking for the vectors T1 and T2, and we want to know their size, their length. How are we going to do it? Well, we're going to use right triangle trigonometry. So here we go. If you remember the right triangle trigonometry we talked about in section 7.1, let's look for oh, geez, what am I trying to say here? The horizontal vertical components. Yeah, exactly. Okay, like it says right here. What's T1 and what's T2? So let's look at T1 for a minute. I'm going to try to zoom in and keep this all together. There we go. So we basically got a right triangle right here. Right triangle. This angle is 50 degrees. And it's 50 degrees. So what we can use is basically use SOHCAHTOA to find what these vectors are going to be. So in the I direction, this is going to be the I direction, and this is going to be the J direction, right? I direction, J direction. So we can see that the vector T1, which is going this way, is going to be the length of T1 times cosine 50 degrees, but it's going to be in the opposite direction of I. So let me erase some of that so it's not too messy. Yeah, so remember I is going this direction. That's the positive direction, this way. And if we want to find this component, the horizontal component, which is basically this piece, hold on, move this out of the way. Hold on a sec. Here we go. If we want to find this piece right here, that's going to be given by the opposite of the length of T1 times cosine 50 degrees times I. And really it's from what's cosine? Cosine is adjacent over hypotenuse, right? Adjacent over hypotenuse. So one thing I want to point out here is that this piece right here, this is where SOHCAHTOA is coming into play. So this, remember cosine is adjacent over hypotenuse. So cosine would be, oops, wrong button. Let me do this. Come here, come back. There we go. Let me look at this piece right here. Here's A, and then here's T1 up here. So if I wanted to solve for A, I would use cosine, and I would say cosine of 50 is adjacent over hypotenuse. So maybe I'll write that here. Cosine of 50 degrees is A over T1, but I'm sorry, the length of T1, right? The length of T1. So really I'm talking about the length of A. So the length of A over the length of T1 is the length of T1 times cosine 50. But we're in the opposite direction, the opposite direction of that basis vector I, and that's where the negative comes into play, right? So that's basically the magnitude in that direction, and then I gives you the basis unit vector. And then we do the same thing for J direction. So if we wanted to find this right here, we use SOHCAHTOA again, and we'll get that. And so that's how we can write the vector T1. It's the sum of those scalars of those basis vectors. That's what we do for T1, or I'm sorry, T1 and T2. All right, let me erase some of this so you can get another look at it. Oops, come back. There we go. And so that's how we do it. So we found expressions for T1 and T2, but they're in terms of the length of those vectors T1 and T2, which we don't know yet. We have to find what the lengths of those two vectors is. And this is where the other information comes into play. So here it says that the weight is 100 pounds. So there's basically 100 pounds of force pulling that way on the wires right here, pulling this way on the wires. But the weight is suspended there. The weight is suspended there. So the sum of these two vectors is counterbalancing the weight. It's counterbalancing the weight. So the sum, T1 plus T2, is giving you the opposite force of that weight, 100. So we can write this. We can say that the sum of those two is going to be the opposite of that force W, and W is in the J direction, but it's in the it's pointed down, so it's in the negative J direction. And these two forces, the forces T1 and T2, are basically pulling upward on it. So that means that the sum of those two is going to be in the opposite direction of W, which is given by 100 times J. 100 times J. And that's where we get this equation. Come here, there we go. And this equation is essentially the equilibrium equation, right? So the 100 times J is equal to the sum of those two vectors, and everything's being counterbalanced because nothing's moving around. Now we're going to get a very messy result, but we can combine like terms, and we're going to get this. We're going to get 100J equals this times I plus this times J. And that's it right there. Next, what we can do is we can compare coefficients. So let me re-highlight this. Notice this is 100J, and there is no component in the I direction on this side of the equation, right? There's no horizontal displacement going on when the weight is pulling straight down. So what that means is that if we compare coefficients, there's like a 0I over here, 0I plus 100J. And because we know that 0I plus 100J is going to be this mess times I plus this mess times J, we know that this first mess must be equal to 0. So first mess is equal to 0. And we know that the second mess right here, that must be equal to 100. So second mess equals 100. That's the idea. Now, let me erase this real quick. If you kind of look at the structure that we've got here at the bottom, this is a system of two equations in two unknowns, which means we can solve for the unknowns precisely. So our unknowns are length of T1, length of T2. Length of T1, length of T2. Those two quantities appear in both equations, and we have two different equations that relate them, which means we can use either substitution or elimination and solve for both of these values. In this case, I'd probably recommend elimination, but you basically go through a bunch of algebra and you will get these results. So the length of T1 is this. Then when you can use a calculator or a computer to approximate it, and we get 85.64. That's the length. And then, or the magnitude, I should say, the magnitude of the force. And then, yeah, not the length, the magnitude of the force. And then what's T2? The magnitude of T2 is going to be this value, and again, you could use a calculator or a computer to get an approximation, and it will give you 64.91. Now that we know the magnitude of those two forces, we can describe the forces at least approximately because we approximated. So the force T1 is this much in the direction I, this much in the direction J, and the force T2 is this much in the direction I, this much in the direction J. And that's it. One thing I'll point out, which makes sense, again, if you think about it intuitively, which I encourage you to do, notice that the magnitude of the forces in the I direction cancel each other out, which makes sense because the weight is not going to fall to the left or fall to the right. It's not falling to the left or the right. So those two wires are basically pulling on each other horizontally in exactly the same magnitude but opposite direction. That's why they're the same size but opposite sign, you could say. And yeah, just another note about intuition before I end the lecture here, because we're about done. You should try to keep intuition through all of this, because when you get into your physics classes and your engineering classes, your chemistry classes, the intuition can guide you. The mathematics here is supporting your intuition. So when you get a result, you should do a sanity check and be like, does that make sense in the context of my problem? Yes, it does make sense in the context of my problem, especially what I was just saying here, right? That those two forces are equal in size but opposite direction. There you go. Whew, okay. All right, now let's play. So that is our discussion of vectors. Uh, Again, I just want to say, thank you for bearing with it. I know that it's a long lecture. It's a lot of stuff. If you had to pause and take breaks, that's great. Don't feel like you had to grind through it all in one long session or anything. That's totally fine. But I did want to merge these two sections because again, this all these ideas are totally general. You can apply these to any dimensional vectors. It doesn't have to just be 2D and 3D. All right? So I'll stop there and I'll see you next time when we talk about the dot product. Have a good day.